All right, so let's take a look at some additional examples here of using implicit differentiation, because we've only seen a few examples of this so far, and I want to go on with that. And then after we've done a few more examples of that, what I'd like to do is to look at taking derivatives of inverse functions, which we're actually going to derive the derivatives of inverse functions in two different ways. One of them using implicit differentiation, and one of them using a really, in my opinion, kind of more enlightening argument, actually, that for some reason I don't see calculus textbooks using, but I actually think it's a nicer way of understanding what's going on. But first, more examples of implicit differentiation. So I want to kind of emphasize to you once again, the key point when you do this is that if you treat one of the variables as the independent variable, that's the one that you differentiate with respect to. All the other variables have to be thought of as behaving like functions, okay? And so I want to do some examples where instead of using x and y, we are using other variables. So let's suppose that we want to find r prime dr by dt. Sorry, that does not look much like a t. That doesn't look much like a d either. In fact, the entire thing was kind of a mess. There we go. R prime equals dr by dt, given the following sort of relationship. So let's suppose that we have r squared t plus, let's say, t times the sine of r is going to be equal to, let's say, let's do r times t to the minus 1. I don't know. Again, I'm just kind of making up this example for the sake of running through something. So what we're going to do here is r is going to be the dependent variable here. We think of r as dependent upon t. Therefore, if I differentiate with respect to t, I have to actually treat r like a function. And that means applying the chain rule. This is the part that I see students often get themselves a little bit hung up on. People forget when they're doing the derivatives of the dependent variable, they treat it just like it were the independent variable. And so they end up losing some very important factors. Okay, so let's carefully work through this problem. In fact, let me suggest that before I work this, you pause this for a minute, try to work this yourselves, and then watch what we do together and see if you did the same thing to make sure that you did it correctly. So, okay, what I'm going to do here is I'm going to just apply the derivative on both sides. So, sorry, I know that's a little bit messy, but d by dt, hopefully everybody knows what that is. Now, when I take the derivative of r squared t, this is going to be something that requires the product rule. This is going to give me the derivative of r squared times t plus r squared times the derivative of t. And then this, now the thing about this is, and I don't want to just write this whole thing out because it will be very long and messy, but what I want to emphasize is what's going to happen here. When I take the derivative of r squared, it's not the derivative with respect to r, it is the derivative with respect to t. So the derivative of r squared is actually going to be 2r r prime. That r prime is really important, and it comes in because this is the dependent variable, not the independent variable. Okay, and that is really, really crucial. 1 second here. Okay, sorry about that. So that is where the r prime is coming from. Now, when we do the derivative of t, we do not get a t prime, or we sort of do, but the thing is, like t prime, the derivative of t with respect to t is just 1. So this derivative of t, this just becomes t. So we have 2r r prime t plus r squared, 1. It becomes 1, not t. Now, for the next term, the same kind of thing applies. The derivative of t would be 1, and then the derivative of sine of r is going to be r prime cosine r. And on the right-hand side, we are going to get r prime t to the minus 1 minus r t to the minus 2. So again, the point here is that we have to continually, anytime we are taking the derivative of something other than the variable itself that appears in the differential operator, remember these d by dt's or d by dx's, those are known as differential operators. Anytime we do that and it's not the variable that's in the operator, we have to think of it as if it's like a function and apply the chain rule. And so every time I do that to an r, it's going to pick up an r prime. Because, of course, the chain rule always gives us something times the derivative of the function. And that's the thing that I think people tend to forget. They tend to drop their r primes a lot. Or, if it's x and y, they tend to drop their y primes, their dy, dx's and things. So just try to keep in mind what you're doing here, that when you differentiate one variable with respect to another, if you don't just have an expression for it, then what you're going to end up doing is you're going to end up having to tack on one of these things via the chain rule. Now, at this point, we've done all of our derivatives, so all I need to do is to solve for r prime. And it's going to be a solution that involves both r's and t's, but that's okay. There's no issue there with that. So if I gather all of my r primes on the left and factor the r prime out, I will get r prime times 2rt from this term. And then we're going to get this term, which is a t cosine r. And then we're going to get this term, which when I move it to the left gives me minus t to the minus 1. And I'll move everything else to the right, so this is going to give me negative rt to the minus 2, and then it's going to give me minus r squared, and then minus sine r. So now what we can do is we can just divide both sides, and we have r prime. So here we go. R prime is equal to, I can factor out a negative and say this is negative rt to the minus 2 plus r squared plus sine r. And this negative is applying to the whole fraction here, not just to the first term. That's where I'm factoring out the negative. And then in the bottom, I have 2rt plus t cosine r minus t to the minus 1. Now, depending upon what you want to do here, some people might say, okay, well, we should multiply we should multiply through by a t squared or something to help simplify this, get rid of the negative exponents. I don't really care too much about that. If you leave it like this, whatever. If the homework gives you a problem with this, then I give you plenty of attempts to enter it in a slightly different form. But if it doesn't seem to be working for you, just let me know, and I'll go through and manually fix whatever it's telling you is wrong. Although, obviously, if you actually got it wrong as well, then I can't do that. If you have the right answer, but they just are mad about the formatting for some reason, then I'm happy to fix it. So, that's the important thing. When you're differentiating one variable with respect to another, and you're doing this implicit differentiation thing, we are really treating r like a function of t, so it needs to have an r prime come in every time we do the derivative. We need to use the chain rule. Now, one of the things I want to observe here is we can actually find higher order derivatives using these implicit differentiation techniques as well. So we haven't really seen that yet. We've only been doing first derivatives. And I want to, at this point, go ahead and take a look at a second derivative. Let's start with a fairly straightforward case. Let's suppose that we want to find the second derivative with respect to x of y, given x squared plus y squared is equal to 1. So this again is just the unit circle. We started out our implicit differentiation stuff with an example using the unit circle. I figure we may as well come back to that again. So if I differentiate both sides here, Well, we've done this before. So we'll go through it pretty quickly. Here, this is going to give me 2x plus 2y, y prime is equal to 0. And this gives me y prime is equal to negative x divided by y, which I can also think of as negative x y to the minus 1. Now, what I'm going to do is I'm going to take this expression and differentiate it once again with respect to x in order to get the second derivative of y. Because now I have the first derivative, I can take a second derivative. So what is, let's write this down over here. The second derivative is going to be d by dx of negative x y to the minus 1. Well, that is going to be negative y to the minus 1 plus x y to the minus 2 times y prime. So this is where, once again, do not forget that when you differentiate with respect to y, let me rephrase that because I said that slightly wrong there. You may have noticed. When you differentiate y with respect to x in implicit differentiation, you do in fact pick up a y prime. And that's where this y prime is coming from. So we now have the second derivative written in terms of x, y, and the first derivative. But actually, we know the first derivative in terms of x and y alone. So now what I can do is I can take this quantity for the first derivative, I can substitute that where I see the y prime. And I can say this means, and let's write this down at the bottom, we get the second derivative of y is going to be negative y to the minus 1 plus x y to the minus 2 times y prime, which is actually negative x y to the minus 1. So this becomes negative y to the minus 1 minus x squared y to the minus 3. So there we go. We have now managed to find the second derivative entirely in terms of x and y. Now, you can't expect to be able to get this entirely in terms of x's. The reason for that is because, once again, y is not truly a function of x here. It is locally a function of x. That's why we can use implicit differentiation techniques, but it's not globally a function of x. It is globally going to be a non-function, and therefore it is going to give us this derivative stuff in terms of both x's and y's, because for a given value of x, we have multiple possible values of y here. So let's take a look at another example of finding the second derivative of something. Let's suppose that we want to find the second derivative of y given, let's say that we have x times y plus x cosine y is equal to, let's say, e to the x. Well, first we find the first derivatives here. So we're going to take the derivative of the left-hand side, xy plus x cos y equals derivative with respect to x, e to the x. This is going to give me y plus xy prime plus cosine y minus x y prime sine y is equal to e to the x. So that just comes from, again, applying the derivative operator here and using the chain rule every time we differentiate y. So this is now going to allow me to solve for y prime. We're going to get y prime times x minus x sine y is equal to e to the x minus y minus cosine y. And this means we're going to get, and I'm going to write this at the bottom because we're going to have to erase this work that we've done in a moment. Y prime is equal to e to the x minus y minus cosine y divided by x times 1 minus sine y, where notice here that I have factored an x out. And now what I can do, now that I've got this y prime here, is I can differentiate this thing again. So the way that I'm going to do this is I'm going to use the chain rule. I'm going to say my f here is e to the x minus y minus cosine y. That makes f prime into e to the x minus y prime sorry, now I'm a little bit confused. Did I accidentally mess up? No, okay, that's fine. I was confused where this negative came from for a moment, but I found the negative, so we are all good. And so then we're going to have plus y prime sine y. Then my g is going to be equal to, we may as well just write this as x minus x sine y. So you'll notice I factored an x here, but to take the derivative, I may as well unfactor it. Because then g prime is going to be equal to 1 minus sine y minus x y prime cosine y. So now we put all of this stuff together and we can say y double prime is going to be f prime times g. So that's going to be e to the x minus y prime plus y prime sine y times x minus x sine y. And then we're going to have minus fg prime. So that's going to be e to the x minus y minus cosine y times 1 minus sine y minus xy prime cosine y. And you can see this is quite the lengthy thing here. And then in the denominator, we're going to have x squared 1 minus sine y squared. And now, the last step for this problem, which I'm not going to write down in full because it would take up more room than this whiteboard has. The last step then is just take this expression and plug it in for y prime. So every time a y prime shows up, you plug in this expression. Now, this problem that we just did is really, really long and complicated. It gives us an annoyingly long answer. Fortunately, most problems that you do like this are not going to be nearly this long, but I wanted to show you one where things get rather complicated and messy. Hopefully, most of your examples will not be quite this complicated and messy, but the point is we can handle it if it gets that way. We can absolutely do it. And if we do that kind of thing, well, that is going to allow us to find these derivatives that otherwise we wouldn't be able to. Now, what I want to talk about next is how can we use this kind of idea to help ourselves find the derivatives of inverse functions. So remember what an inverse function is. An inverse function is a function with the property that f inverse of f of x is equal to f of f inverse of x is equal to x. So the inverse function is the function that goes backwards. And there's some special properties we need to remember. In order to get an inverse function, you have to have a one-to-one function. Otherwise, you can't flip it around, so to speak. But if you do have a one-to-one function, you can always construct the inverse function. Now, I'm going to show you the way that the book does the derivative of an inverse function is they use implicit differentiation. The problem with doing this is to do implicit differentiation, you have to assume the derivative exists. And I don't think that it's not necessarily obvious why the derivative exists if you do it this way. But let me just show you what they do in order to do this. So what they do is they take this expression here. So they note that if we take the derivative of f composed with f inverse of x equals the derivative of x, then what we get on the left from the chain rule is f prime composed with f inverse of x times the derivative of f inverse of x. And on the right-hand side, we get 1. So what we end up with is that the derivative of f inverse of x, I can solve for it, and I get it is 1 over f prime evaluated at f inverse of x. And there we go. We've got the derivative by using implicit differentiation. Now, the thing is, though, we haven't justified that this derivative exists. So I want to show you a slightly different way of seeing this. And when we do this different way of seeing it, it will also guarantee that the derivative has to exist. Now, there is one other thing that I want to note. We don't normally, I wouldn't say, just use this formula. We usually just derive it every single time by using implicit differentiation. That's because it's often easier to just do that than to use this formula. But you can just use this formula. And we might do that a little bit here to sort of see some of these problems. So here is my alternative. Remember that df by dx, this is actually equal to, well, actually, let me put it this way. Let y be equal to f of x. Then x is equal to f inverse of y. So let me suppose now that I want to find df by dx. Well, this is actually the limit as delta x approaches 0 of delta y divided by delta x. And we are supposing that this exists. But by a similar argument, the derivative with respect to y of f inverse of y, this is the limit as delta y goes to 0 of delta y over delta x. Now, because f is continuous, delta y going to 0 and delta x going to 0 are the same things, as long as the derivative with respect to x is not 0. If that were 0, then we have some complications here, because then maybe you don't actually have any changes in y at all or something like that. But as long as this derivative is non-zero, then this is actually just equal to the limit as delta x goes to 0 of the reciprocal of delta x over delta y if delta y is not equal to 0 for small delta x. But this is actually just the reciprocal of this derivative. And so what we find is that the derivative of f inverse at y is actually just f prime of x. But if you rewrite that, what you end up with when you change all the variables around is you end up with exactly this formula. Okay, so this formula is identical to what you get when you use this method of derivation. And to switch out the variables, what you have to notice is that, well, this is actually going to be, I don't have room to write it over here, so let me write it over here. This is going to be 1 over f prime of x, which is actually equal to 1 over f prime composed with f inverse of y. But this is actually the derivative of f inverse at y. So to get from this formula down to this formula here, all we're doing is we're interchanging the variables x and y. We're just renaming the variables. Because normally when we flip a function around to get the inverse function, we switch the roles of x and y. And well, so it's a bit of a complication. It's a little annoying to do that, but that's all that's going on there. This also illustrates that this only really works and it's justified under certain circumstances. So there will be cases, in particular, when my derivative is equal to 0, then the inverse function won't have a derivative. The reason I like this method instead of using the implicit differentiation and chain rule is because it really geometrically makes a lot of sense. Because let me show you the geometric significance of this kind of thing. Geometrically, if I have some curve, here's my y equals f of x. Well, the change in y per change in x, I'm really looking at what is, here's my change in y, here's my change in x. I am looking for this slope as we take this smaller and smaller and smaller, and that's going to give me my tangent line. However, when I do that, if I were to look at the inverse function, see, I can also think of this as x is equal to f inverse of y. But if I take, if I look at the derivative of this with respect to y, it should end up giving me exactly the same tangent line geometrically. Which means that it's going to have to be, when I write out the tangent line in terms of x is equal to some slope times y plus a constant, well, that slope is going to have to be the reciprocal of the slope when I get it in terms of, the usual way, y is equal to some slope times x plus a constant. So because these tangent lines should come out the same way, whether I calculate the tangent line in terms of, in other words, what we're going to get is we're going to get that the tangent is going to look like y minus y0 is equal to f prime of y0 times x minus x0, but also it should be equal to x minus x0 is equal to f inverse prime evaluated at x0 times y minus y0. Well, when you compare these two values, you'll see that the only way that these can be true, the only way that these equations actually give me the same line, is if this is reciprocal. You end up pulling in a reciprocal when you do this. And so this argument kind of shows us geometrically what's going on. It also shows us why this should be differentiable. The idea is that if I can take the limit of delta y over delta x, then as long as as long as those aren't both 0, or as long as, the delta y isn't 0 as we take delta x down to 0, as long as it's just approaching 0, then when we flip it over and take the limit, we should just get the reciprocal of that limit. So it's exactly what we would expect. Well, sort of. I mean, maybe you wouldn't have expected that ahead of time. But what I want to show you with this is that if you didn't know what the answer should be, you could play around with this geometrically and you could argue, oh, yeah, that actually is exactly what it should be. See, because what happens when you take the inverse? You're interchanging your x's and your y's. Well, when you do that, your slopes get reciprocal. They get flipped upside down because your slope of your tangent line is your change in y per change in x. If I interchange those two variables, if I switch which one is the dependent and which is the independent variable, that should just flip that change in y over change in x to a change in x over change in y, and it's the reciprocal. So let's take a look at how you can use this formula or these ideas to find some particular derivatives of inverse functions. And the first one I want to look at is what is the derivative of the natural log of x? Well, what we know is that this should be equal to 1 over the derivative. If I let f of x be equal to log x, this should be 1 over f prime composed with f inverse of x. So this is going if I let f of x be equal to e to the x, that's what I want to do, because this is my f inverse. F inverse of x equals natural log x. So if I do this, then this is going to be 1 over e raised to the natural log of x, but that is just 1 over x. So the derivative of the natural log is 1 over x. We can also see this by just sort of directly using implicit differentiation. If I were to differentiate e to the log x, that has to be equal to the derivative of x. So that gives me e to the log x times the derivative of log x equals 1. That tells me the derivative of log x is equal to 1 over e to the natural log x, but of course that's just 1 over x. So we can use implicit differentiation directly to get this, or we can use the formula that we just worked out before. This is kind of interesting because notice this is actually x to the minus 1. And if you think back to our power rule, well, the power rule can give you x to any power as a derivative except x to the minus 1, right? Because the power rule says that the derivative of x to the n is n x to the n minus 1. Well, the only thing you cannot end up over here with then is an x to the minus 1, because in that case, you don't actually have any sort of, then it's just multiplied by 0 and it goes away. And in that case, you're taking the derivative of a constant. So, what we can then say is that this is sort of a special case with powers of x. This power of x shows up as a derivative of the natural log function. Now, using this, we can also figure out what is the derivative of any logarithm. And by the way, we can also figure out, using the chain rule now, what is the derivative of any exponential. So let's just quickly go through how you do that. If I wanted to take the derivative of a to the x, I can remember that this is actually the derivative of e to the x times the natural log of a. This is going to be natural log of a times e to the x natural log a, which is natural log of a times a to the x. So when you take the derivative of a to the x, you pick up a factor of log a. By the way, when I say log, I mean natural log, unless I specify otherwise or it's very clear from context. Usually, if you're talking to a mathematician and they say the word log, what they mean is natural log. If they, like some other people, they will say log when they mean log base 10. But we mathematicians usually like to work with natural logs. So when we say log, you can usually assume it's a natural log. By the way, this also shows that the limit as h goes to 0 of a to the h minus 1 over h is equal to the natural log of a. Because you'll remember, this is the factor that shows up in the derivative of a logarithm. Or not the derivative of a logarithm. What on earth am I saying? In the derivative of an exponential function. So the derivative of a to the x is log a times a to the x, but it's also this limit times a to the x. So those two numbers had better be the same thing. Now, remember that we can also use our limit conversion to rewrite any given logarithm in terms of a natural logarithm. So let's sort of briefly remember how that works. Remember, if I want to do the log base a of x, well, a to the log base a of x is equal to x. But this means e to the natural log of a times the log base a of x is equal to x. And this means that the natural log of a times the log base a of x is equal to the natural log of x. I've just taken the natural log on both sides. So this means that the log base a of x is natural log x over natural log a. Maybe you already remembered that from before, but I don't expect you to necessarily remember that formula, and so I figured I should rederive it for you here really quickly. So if I want to take the derivative of the log base a of x, well, this is actually going to be equal to the derivative of natural log x over natural log a, which is just going to be 1 over x times the natural log of a. So we're able to figure that one out now using the chain rule. We don't have to worry about using the special properties of the logarithm function here. We could work this out by saying, oh yes, a to the log base a of x is equal to 1, and then let's calculate what ends up happening, and so on and so forth. We don't actually have to do that here, although we could. So there we go. Now, of course, we can use this with any other rule that we have, okay? So for instance, one of the nice things we can do is we can work out the following really cool formula. If I need to use the chain rule on a logarithm, so let's say that I have the log of f of x, this is going to be 1 over f of x times f prime of x, which is actually just f prime over f. So you can use the chain rule very easily, and this is another one of those special cases of the chain rule that comes up often enough you may want to memorize it. The derivative of a natural log of f is f prime over f. For example, if I wanted to do the derivative of natural log of 3x squared minus 2 divided by 5x, I can say, well, this is going to be, actually, let's just do 3x squared minus 2. That's enough for this example. You could throw in that extra complexity, but it doesn't really illustrate what I want to show you any better, I don't think. So this is just going to be f prime, which is 6x, divided by 3x squared minus 2. And there we go. That is the derivative. It's a really interesting thing here, also notice, because what we're seeing is that derivatives of logarithms of polynomials are always going to give you some kind of rational expression. So there is this very close relationship, actually, between logarithms and rational expressions. In fact, we already saw that, of course, because the derivative of natural log is 1 over x. And there is another whole approach to defining exponentials that is done by exploiting that relationship. And we'll mention that briefly in a month or so when we start talking about some other things. I will mention how some people actually use this relationship to define the logarithm. They define the logarithm to be a function whose derivative is 1 over x, together with saying that the logarithm at 1 should be equal to 0. And then they get all the usual properties of the logarithm out of that. The nice thing about doing it that way is that you automatically get that the logarithm is differentiable. And then you automatically get that the exponential is differentiable because the exponential is just the inverse to the logarithm. So yeah, there's sort of this, you could do it that way if you wanted to. And some people like to do it that way because it makes it easy to see that logarithms and exponentials are differentiable. Anyway, let's move back to the problem at hand. So let's see if we can work out some other types of derivatives of inverse functions. One of the other types of inverse functions that we're used to working with are trig functions, right? We want to take derivatives of trig functions, or inverse trig functions sometimes, perhaps. So what if I wanted to do the derivative of inverse tangent of x? Well, the way that I'm going to do this is I'm going to work this out by saying this is going to be equal to, now my f of x here is going to be tangent x. F inverse of x then is tan inverse x. We have to be careful at this point. Be really careful. we have to restrict the domain to minus pi over 2 up to pi over 2. Whoops, sorry, not square brackets, open brackets, because this is tangent. So we do need to have a restricted domain. And the reason I got to restrict the domain is because, let's close this door because I'm not sure how well you can hear that stuff out there. The reason I got to restrict the domain is because otherwise this is not a one-to-one function. Anyway, when I do this, then f prime is secant squared x. Fairly straightforward. We know that that's what that comes out to be. So this derivative is going to be 1 over f prime, which is secant squared, evaluated on f inverse. So this is secant squared of tan inverse x. But although this is true, we can actually do something even more useful. We can write this in a nicer way. And the reason for that is because we can evaluate secant at tangent inverse x. Why? Well, draw a triangle here, a right triangle, with an angle theta where the tangent of theta is equal to x. Tangent is opposite over adjacent. So if I put an x and a 1 here, then tangent theta is equal to x. Actually, I'm sorry. I'm doing this rather poorly. No. I'm sorry. That is exactly what I want to do. So what this means is that theta is tan inverse of x. Next, what I can do is I can say, okay, that makes this hypotenuse into the square root of 1 squared plus x squared. I'm sorry, my hypotenuse notation there got a little screwy looking. So now, what can we say about the secant? Well, the secant is the reciprocal of, which one is it? It's the cosine. So what this means is, I don't have any space, that's one of the things that this means, but if I write this out, this is actually 1 over, now, the cosine here would be the, so another way of thinking about it, let me say it this way, the secant is hypotenuse over adjacent. So this is 1 over the square root of 1 plus x squared, which is going to be 1 over 1 plus x squared. There we go. We have got our derivative of the arctangent. But wait a second. This is another example where our derivative came out to be a rational expression. So that's really interesting. It turns out that, once again, this is not a coincidence, because it turns out that there is a really close relationship between exponentials and trig functions, and as a result, there is a very close relationship between inverse trig functions and logarithms. What is that relationship? Minor tangent here, so to speak. Not a tangent as in a trigonometry tangent, but a tangent as in we're going off on a different topic for a moment. Well, what I want to say is that there's this identity. It is not really obvious, but it's a very important identity known as Euler's identity. And I'm not sure if Euler was the first person to realize this or not. This is the complicated thing. Sometimes, see, we got to differentiate, we have, not differentiate as in derivatives, but differentiate as in we have to be able to tell the difference between which identities we're talking about. So sometimes we name an identity after somebody who used it a lot, but they're not always the first person to realize it, okay? So Euler definitely worked with this a lot. He definitely came up with why is this true, but I cannot guarantee that he was absolutely the very first person to know this or something like that. Sometimes we end up with some really wacky naming conventions that come out of sort of nowhere. Euler's identity says, if you allow yourself to involve complex numbers, e to the I theta is equal to cosine theta plus I sine theta. In other words, the cosine of theta is the real part of e to the I theta, and the sine of theta is the imaginary part of e to the I theta. There's a lot more that we can say about these relationships, But that shows us this, yeah, there really is a connection here. And the reason why this is true, by the way, is because what you want to have happen is you want to say that d by d theta, e to the I theta, this should equal I e to the I theta. Well, if you take the derivative of this, that is exactly what you would end up with as well. So these really do give you the same derivatives, and they do both agree when theta is equal to 0. You get 1 equals 1. So therefore, these really ought to be the same function. That's sort of the argument for why this should be true. Now you have to justify, can you really just take the derivative like that? The answer is yes, you can. But it takes a little bit of work to justify it. We're not going to go through that now. We're really going a bit off topic here. But I thought that I would show you this and why it is true. And notice, by the way, the reason that this comes out to be true is because the derivative on this side, this would be minus sine theta plus I cosine theta. But that's actually this expression multiplied by I, because if I multiply by I, this becomes I cosine theta plus I squared sine theta, and that's just a negative sine theta. So they have the same derivatives. They both obey the same derivative property, and they both agree at a certain point. It turns out that in that case, they actually have to be the same function. Okay, so moving back to taking derivatives of inverse trig functions, here's what I would like you guys to do. I want you to take a moment and see if you can work out the derivative of cosine inverse x for me. And remember that in this case, what we're going to do is we're going to say our f of x is equal to cosine of x restricted to 0 up to 2 pi. And our f inverse of x is, I'm sorry, not 0 up to 2 pi. What? I'm 0 up to pi. I threw in a factor of 2 for no good reason there. And our f inverse of x is going to be cosine inverse of x. So see if you can work this out. And don't just work it out in terms of trig function as an inverse trig function. See if you can work it out in terms of x's. All right, so how did that go for you? So this is going to be 1 over cosine, or not cosine, 1 over negative sine of cosine inverse x. But now what I can do is I can set up a triangle here where my angle theta has, I want cosine theta to be equal to x. Well, the cosine is adjacent over hypotenuse, so I put an x and a 1. That makes this side into square root of 1 minus x squared. So this is actually negative 1 over square root 1 minus x squared. We can find the derivative of inverse sine in a similar manner, okay? And I will then leave it to you to, well, you can look in your book too, to see the derivatives of the other 3 inverse trig functions. But the derivative of inverse sine, in this case, my f of x is going to be sine x. Our interval is going to be minus pi over 2 up to pi over 2. And our f inverse is going to be sine inverse x. So this is going to be 1 over cosine of sine inverse x. Set up that triangle, almost the same thing, except this time I want the sine to be x. So this should be x and 1. This should be square root 1 minus x squared. This is going to be 1 over square root 1 minus x squared. And then you can work out the other 3 using a similar kind of argument. Okay, so this video has gone on quite a while here, and I don't really want to keep on going too much longer here. I want to give you guys a little bit of a break, but my previous video was quite short. That's why we needed to take some extra time here. So I'm going to end this here and just say, remember, now that we have this, we can also do all kinds of, like, we can use the chain rule with these things. We can use the power rule. We can use, I'm sorry, the power rule doesn't apply to these, but we can use the product rule. We can use the quotient rule, all of those types of things. All right, so like I said, I'll give you guys a little bit of a break and we'll come back to doing more stuff in a bit.